All right, today we're talking about Chapter 5, Section 1. Yeah, Chapter 5, Section 1, uh, rational expressions and rational functions. So we have previously introduced polynomials and polynomial functions. The ratio of two polynomials defines a rational expression. This leads to the following definition of a rational function. So let's snip our definition of a rational function. So a function is a rational function if it can be written in the form f of x is equal to p of x over q of x, where p and q are polynomial functions and q of x is not equal to 0. Right? So all this basically is basically it's kind of like saying a fraction, right? We're talking about fractions, except we're talking about fractions in terms of polynomials. We'll have a polynomial in my numerator and a polynomial in my denominator, and that's it, right? That is the definition of a rational function. Let's see. So in this course, we restrict our discussion of functions to defined by y is equal to, sorry, my computer's messing up a little bit. In this course, we restrict our discussion of functions defined by y is equal to f of x to those whose domain and range are subsets of the set of real numbers. Therefore, the domain of a function is a set of real numbers that when substituted into the function produce a real number. For a rational function, we must exclude values that make the denominator 0. To find the domain of a rational function, we offer these guidelines. So step 1, we need to set the denominator equal to 0 and solve the resulting equation. And then step 2, the domain is the set of all real numbers, excluding the values found in step 1. So example 1, evaluating a rational function. Yeah, I know I didn't snip everything there. All right, so let's just wouldn't necessarily this is all calculator work, but I'm gonna snip A anyways because it is a lot of computation, but it's computation just plug and chug there. So we'll just snip that as well. But anyways, so given g of x is equal to 2 over x minus 3, let's determine the function values if possible. So this says g of 0, g of 1, g of 2, g of 2.5, g of 2.9, and so forth. All we're doing is plugging these numbers that we see in parentheses. We're plugging those numbers in for x, right? So for instance, if we plug in a 0 for x, we'd have 0 minus 3, which is negative 3. 2 over negative 3 is a negative 2/3, which we see over here. If we plug in a 1, 1 minus 3 is negative 2. 2 over negative 2 is a negative 1, which we see here. And that's how every one of these are done. You just plug the numbers in, and that's it, right? So that's A. B reads, write the domain of the function. Okay, so the domain of the function, we need to, in order to, so looking here, so find the domain of a rational function. So in order to find the domain of a rational function, step 1 says set the denominator equal to 0 and solve the resulting equation. Okay, so this is B. Set the denominator equal to 0, so x minus 3 is equal to 0. And then it says solve the resulting equation. So if we solve, we get x is equal to 3. Okay. Now, step 2, the domain is a set of all real numbers excluding the values found in step 1. So the value that we found in step 1 was x is equal to 3. So step 2 says the domain is a set of all real numbers excluding that value I found in step 1. So the domain of B is going to be all real numbers, and I'm not sure how they want us to write it. It didn't say. Okay, so we're just going to write it in interval notation. Oh, they do it in both. Okay, so let's move this up a little bit. Okay, that's not what I wanted. Let's try it again. Okay, so there are two ways to go about writing the domain here. All right, One way to go about it is interval notation. Interval notation is just basically looking at it on a number line, right? So you're going to say from negative infinity all the way to the number, right? The number being 3, right? And we're going to put a parenthesis here, which means that we're not including the number 3. It's going to be unioned with 3 to infinity. Okay, so this is basically the intervals from negative infinity to 3. We don't include the number 3 because that's what we say right here, right? We don't include it because, again, step 2 says the domain is a set of all numbers excluding that value that I found. Okay. Anyways, we're going from negative infinity to 3, union with 3 to infinity, right? That is interval notation. And then set builder notation, you're just going to say, and let's make a better brace there. You're going to say x, because that's the variable, x such that, the vertical line means such that, x such that what? X cannot be equal to 3. Okay, those are 2 ways to write the domain here. The one on the left is interval notation, and the one on the right we write in set builder notation. Set builder notation, in my opinion, is, I just like it's cleaner, right? X such that x cannot be equal to 3, which makes sense if we look at our function here. If we plug in a 3 into our function, we get 3 minus 3, which is 0, right, which is undefined, which of course we see here, right? We're actually asked at one point to evaluate g of 3, and we get 3 minus 3 is 0, 2 divided by 0, that is undefined. Right, so the domain is every number but the number 3. Okay. So example 2 reads, write the domain in set builder notation and in interval notation. So what we need to do, again, we need to set the denominator equal to 0. So let's go ahead and do that. Start with a. Set the denominator equal to 0. So we've got 2x squared minus 11x plus 5 is equal to 0. All right. Now, let's actually try to compute this using the AC method. I don't think we've went over the AC method in this course yet, though. Yeah, I don't think we have. Oh well. So I'm going to let's do this on the next page. The AC method. We might have. I don't know. These courses run together. But the AC method is whenever we do a quadratic equation, we have ax squared minus what in this particular case it's just plus bx plus c, right? That's a quadratic equation, right? So when we talk about the AC method, a is the leading coefficient and c is just a constant. Okay, so we're going to say 2 times 5. All right, AC. Let's do this better. AC method is a times c, or in other words, 2 times 5, which is equal to 10. Okay, and I probably should have erased this first. So give me a second. I have to tediously erase this, and since I can't just hit the back button. All right, that should do it. Okay. So next up, what we're going to do is we're going to look at the number 10, and we're going to look at all the factors of 10. All right. So, and of course, in this we're looking for the positive components of it, right? And I'll discuss that as examples come to fruition here. All right. So 10. So 1 times 10, 2 times 5. Well, that's it. All right. 1 times 10, 2 times 5. All right. So this we did the AC part of the AC method. The next part is we're going to say, okay, so of these factors, which pair, when you add or subtract them together, will give you a negative 11? Okay, well, obviously, I say obviously, a negative 1 and a negative 10 will give me a negative 11, right? So having both negative 1 and negative 10 will give me a negative 11. And of course, negative 1 times negative 10 is indeed equal to positive 10. So this works. So let's write this. We're going to say 2x squared. And let's just go ahead and write minus x minus 10x plus 5. Okay. All right. So once we do that, notice how negative 11x, right, is the same thing as negative x minus 10x, right? Negative x minus 10x is still equal to negative 11x. So we haven't changed the value of this function at all. All right, all we're doing is just rearranging things to make things a little bit easier to work on. Okay. Next thing we're going to do is we're going to factor by grouping. All right, factor by grouping. So we're going to group the left side and the right side up. So if I factor the left side here, what can I factor out of the left side? Well, it appears that I can pull out an x, and what remains to be a 2x minus 1. What can I factor out of the right side? All right. Well, looks like I can pull out a 5. Okay, but just for the sake of it, let's say we're going to factor out a 5. So 5 is just simply a positive 5, right? So factor out a positive 5, and what remains would be a negative 2x plus 1. Okay. Now here's the thing. In order for this to work, I need this and this to be this exact same. Right? Luckily, there's not too many steps involved here. It's just sometimes you might run into this issue where they're the exact negatives of one another, right? This is a positive 2x, this is a negative 2x, this is a negative 1, this is a positive 1. So what we must do instead of factoring out a positive 5 is we need to factor out a negative 5. So we factor out a negative 5, and that leaves me with a 2x minus 1. All right? So now we can proceed, and my function is 2x minus 1 and x minus 5. Okay. Let's actually write that in blue. Okay. The reason why is because we're going back to this. Okay. So we're essentially actually we'll have to write that in blue at all. But instead, what we're going to do is we're going to proceed on this page. So what was it? 2x minus 1, x minus 5. So 2x minus 1, x minus 5 is equal to 0. And then it looks like from here, I can, what I'm going to do is I'm going to set each one of these equal to 0. So I'm going to set 2x minus 1 equal to 0. And then I'm going to set x minus 5 equal to 0. So I'll have 2x minus 1 is equal to 0, which means if I add 1 to both sides and divide by 2, I've got x is equal to 1/2. And then if I did x minus 5 is equal to 0, I ran out of room. X minus 5 is equal to 0, I get x is equal to 5. Okay. Now, that's what happens when I set my denominator equal to 0, right? And once I set my denominator equal to 0 and solve for it, I get x equals 1/2 and x equal to 5. And then from here, I have to write the domain in set builder notation and in interval notation. So let's go one more page here. So A continued. So what was it? I forget. I'm sorry. 1/2 and 5. So my solution here, if I wrote this in interval notation, would be, I forgot. They're both positive. Okay. Would be from negative infinity to 1/2 unioned with 1/2 to 5 unioned with 5 to infinity. Whew. That's interval notation. Now set builder notation, as I mentioned, is something that I like a little bit more. We're just going to write the curly brace. We're going to say x such that x cannot be equal to 1/2 and x cannot be equal to a positive 5. Right? And that is a written in interval notation. Oops, a little too far. Right? That's that. Next, we're going to do b, and let's go ahead and re-snip the problem here. Okay. So we're in luck on b. We need to set the denominator equal to 0 and then solve. So we have x squared plus 4 is equal to 0. All right, so we've got x squared is equal to a negative 4. Okay, so this is not good though, right? Because there's nothing that I can square that would give me a negative 4. There's nothing that I can square to give me negative 4, right? I mean, a negative times negative is a positive number, so I can't do that. So what this means is the domain of B is all real numbers. I can use every single number. And that makes sense, though, if we look at it. So looking at g of x, there is no number that will make this denominator equal to 0, right? If I put, I mean, again, just if I plug in a 0, 0 squared is 0, 0 plus 4 is 4. Perfect. If we were to say negative 2 squared is positive 4, 4 plus 4 is 8. Okay, there is no number that will make this denominator equal to 0 because there's no number that you can square to give you a negative number, and a negative number plus a positive number will give you a 0. So there's nothing that will make that denominator equal to 0, so the domain is indeed all real numbers. Oh, I guess. Okay, so in interval notation, I'm sorry, I should have wrote that in interval notation. So in interval notation, it is from negative infinity to positive infinity. And then if I were to do set Bill notation, I would say x such that x is an element of the real numbers. Right. That's, sorry, got ahead of myself there. So next up, we're going to need to simplify rational expressions. Right. So in life, it's always easier to simplify anything, right? I mean, if something's complicated, you simplify it. That's all there is to it. So this, let's see, okay. So this particular example, we have a couple of steps. Given the expression 2x cubed plus 12x squared plus 16x over 6x plus 24, we need to A, factor the numerator and denominator. Okay, so this is step number 1 in example 3, but it's also step number 1 in literally everything you're going to do. Always factor, always, every single time. Okay. So if we were to factor here, let's see, let's try something else here. I've been trying out putting things on the right side because I'm left-handed, and it makes it where I can see better. So we're going to go ahead and try to factor out the numerator. So it looks like I can factor out a 2 and an x out of the numerator, right? So I can factor out a 2x out of the numerator, and what remains would be, looks like an x squared plus 6x, and then plus 8. And my denominator, looks like I can factor out a 6, so what remains would be an x plus 4. X plus 4. All right, and that is factoring the numerator and the denominator. All right, next up, B, determine the restriction on x. What that means is, what can my x value not be? Okay, well, in this particular case, if all I have to do is look at my numerator, right? Because my numerator, did I say numerator? Look at my denominator, because my numerator can be anything it wants to be. My numerator can be 1. My denominator cannot be 1. I'm sorry. My numerator, yeah, it can be 1, true, but it can also be 0. My denominator cannot be 0. 100% of the time, it cannot be 0. We cannot divide by 0. Okay. So looking at my denominator here, what can my x be to make it a 0? Okay. Well, obviously it looks like a -4, right? Because if I plug in a -4 in for x, I end up with, and just looking right here, -4 plus 4 is equal to 0. And of course 6 times 0 is 0. So it looks like x cannot be equal to a -4. Okay. So that's the restriction on my rational expression. And then C, simplify the expression. So we need to simplify this. So in order to simplify, let's kind of out of room. Okay, so let's do this on another page. We're going to snip this. And we're going to continue on with C. So C. So in order to simplify, it looks like in the numerator I have a quadratic equation that I can simplify. So let's go ahead and simplify my quadratic in the numerator. So x squared plus 6x plus 4. It looks like I can factor that into an x plus 4 and x plus 2. So x plus 4, x plus 2 all over 6, x plus 4. Well, it looks like my x plus 4 is going to be, I can cancel my x plus 4s. So I end up with a 2x times x plus 2 all over a 6. Okay. And well, yeah, we can simplify that further. The 2 and the 6 can simplify into an x over x, I'm sorry, x times x plus 2 over 3, because that turns to a 1 and this turns to a 3. Okay. And so that is the simplified version. I'm pretty sure that's all we were asked to do. Okay. More, let's see, 5. I think there's only 6. Yeah. So simplify rational expressions. In my opinion, these are pretty darn easy. It's always easier when you don't have any addition or subtraction signs involved, I think, right? So let me make this a little bit larger because I know exponents can be harder to see. I don't know if that helps. You know what? How about this? Let me just rewrite it. So we've got a 2x squared y to the 8th all over 8x to the 4th y cubed. Okay. Well, it looks like this 2 and this 8, right? The 2 turns to a 1, this 8 turns to a 4. It looks like I have an x squared over x to the 4th, so it looks like the x squared up here is gone, and then this x to the 4th turns to x squared. And then down here, this y cubed goes away, and then this y to the 8th turns into a 5. So this is simply a, my numerator, I just have a y to the 5th, so 1 y to the 5th, or just simply y to the 5th. And my denominator has a 4x squared. Right? And that's it. All I did was simply cancel. And again, I mean, if the variables messed you up, just basically just look at what number is larger, 4 or 2. Well, the 4 is larger, so I can take away the 2 and then take that from the denominator. So 4 minus 2 is 2. 8 and 3, which one's larger? Well, 8's larger. Well, I'll take away the 3 from the denominator and get y to the 5th. So that's how we do example 4. Example 5. I just feel like we skipped something. Chapter 5. Either that or I'm just teaching so many courses I forget what all we are going over. Which very well may be the case. Okay, so example 5, I just went ahead and snipped it. It's nothing new. What we do here is we just factor the numerator and denominator. I said that's the first step we do every single time. And when we factor the numerator and the denominator, uh, we end up with t plus 2, the quantity of t plus 2 times the quantity of t squared minus 2t plus 4 all over t plus 2 quantity squared. And then from here, we can cancel out one of the t plus 2's in the denominator with the only t plus 2 in the numerator, and we end up with our equation here. All right. Again, nothing extraordinary. All we did is just simply factor the numerator and the denominator and cancel. All right, and actually, probably let's do this. How do I get this up? There we go. Let's actually. Example 5 was nothing different from the previous examples, but example 6 is. So we'll actually work on this one. Alrighty, so looking at the left here, the left side, when two factors are identical in the numerator and the denominator, they form a ratio of 1. Of course, we know that, right? 3 over 3 is 1, 9 over 9 is 1, smiley face over smiley face is 1. Sometimes we encounter two factors that are opposites and form a ratio equal to negative 1. So, for example, negative 5 over positive 5 is equal to negative 1. Okay? And also a positive 5 over negative 5 is equal to negative 1. And then so notice how each one of these are something over its negative. Right? 100 over negative 100. Now look down here, we have x plus 7 and a negative x minus 7. We have a positive x and a positive 7 in the numerator, and a negative x and negative 7 in the denominator. Okay? By doing the algebra here, what we're doing here, if we look to the right here, we factor out a negative 1 out of the denominator. We end up with x plus 7 divided by, and again we factor negative 1 out, negative 1 times x plus 7. The x plus 7's cancel, so you end up with 1 over negative 1, or in other words, negative 1. Okay, so that's the algebra behind why something over its negative, or it's negative over something, is equal to negative 1. So example 6 reads, simplify the rational expression in lowest terms. So if we simplify this, well, we have an x minus 5 in my numerator. My denominator is 25 minus x squared. Okay, well, that's a difference of squares, right? So I know that that is a 5 plus x times a 5 minus x. Right? Oh, I wrote that wrong. I did say 5 minus x. I just wrote it wrong. Okay, 5 minus x. Alrighty, so let's examine this. In my numerator, I have a positive x and a negative 5. Okay. Well, in my denominator right here, it looks like I have the exact negative of that, don't it? Right? So instead of having a positive x and a negative 5 like I do in the numerator, I have a negative x, which is the opposite of a positive x, and a positive 5, which is the opposite of a negative 5. Okay? So what I can do, or I can say rather, is I can say this cancels with this and put a negative 1 out there. Okay? Or let's say this, times a negative 1. Okay? So then it just becomes negative 1 times 1 over 5 plus x. So my solution would just simply be a negative 1 over 5 plus x. Okay, that's my solution because, again, when I cancel here, bam, bam, it turns to a negative. So there's a negative sign that gets put out front, essentially. Even though I did put it in the back, it 3 times negative 4 is going to be negative 12, right? You put the negative in the front. So that is, which one? So that's how we do that. That's how we simplify ratios of negative 1. And that concludes the lecture on Chapter 5, Section 1.